don't go anywhere. Literally, standing waves. It's not like the Queen on a balcony as opposed to being driven along. That's not what a standing wave is. No, a standing wave is a wave which doesn't transfer its energy anywhere or information. And they're mostly associated with music. For instance, strings. This is a string oscillating. It's being sort of like slowed down by a strobe light so you can see it. But what you have is the oscillations of a string. And this is what produces music. In this case, you have a certain harmonic. Notice that it's not completely flat. There's an overall shape to it. We'll talk about the mixing of harmonics later. So in order to sort of like ease things out, we have this diagram. Quite a nice little diagram of a oscillating standing wave. Now, at both ends of the standing wave, there are nodes, but there are also nodes, these are points where there is absolutely no oscillation, along the length of the wave as well. Even though it would seem rather counterintuitive, parts of the string don't actually move. Other parts of the string move a lot. They're called antinodes. So there's 4 of them, if you can spot them, and 6 nodes, including the 2 at the end. So nodes and antinodes. Rather difficult to draw. The main thing is there is no net transfer of energy in a standing wave. So there's the standing wave again. Now, if you're going to try and draw this, it's a little bit more difficult. I'm going to go over that in a minute. But the first thing to say is that a standing wave is where there is no transfer of energy, but it's caused by 2 waves of the same frequency and amplitude, roughly, travelling in opposite directions. And they meet each other and form a standing wave. Now, in practicality, those 2 waves are formed by the wave and the reflection of the wave from one end, or both ends. You know, like the Mounties, they always get the man in the end. Yeah, I'm not going on with that joke. I'm recording and I'm going to record out. So, 2 waves of the same amplitude and frequency travelling in opposite directions meet and combine and form a standing wave. And we draw this as 2 extremes. So we draw that, which would be the one extreme. Let me say it's that one. There you are. See, wait a minute. Watch the diagram. It's that one, and then we overlay it with the other possible extreme. Wait. That one. There you are. See, so it's the bottom. There you are. So now we've got the 2 extremes of the waves drawn together. But you've got to see that they're 2 different waves drawn, or at 2 different times, I should say. You have the node at the point where they cross, and the antinode, which is the point where you have the most oscillation. There's a lot of noise on this one, isn't there? I should take out the sound effects. Anyway, the wavelength actually goes between 2 of these antinodes. So there are like 3 bumps, 3 antinodes, and between number 1 and number 3, that is the length of the wavelength, because you've laid 2 over each other. So you're looking at one peak to one peak, or one trough to a trough in this case, on a single wave. The other one isn't the same time or wave, so it isn't represented. So the wavelength is always across 2 sets of these antinode bumps. Right. Here's some more practical ones. You can just about see some rather interesting waves being formed on the guitar, which doesn't seem to be a genuine Stratocaster. I'm quite sure. I can't read it really. You can see the bottom E string there vibrating with a strange kind of motion, which is caused by harmonics, and you can see a more usual oscillation in the A string, which is the second one down from the top in the left-hand picture. You can also see all the oscillations and the overviews and things like that there between the blue string in the middle and the red, which would be what it was when it was oscillating. I'm not quite sure what the last picture is supposed to represent. No, you got me on that one. Answers, it's a bass, isn't it? Yeah, but I still don't see any oscillation. Maybe it's meant to move. It's not moving. Okay, so let's look at a string. A real standing wave. That's a string. That's the string in tension. We oscillate it and it vibrates like that. That's its fundamental. That's the basic vibration it does. 90% of its energy usually goes into something like that if you plug it in the middle. And that's its oscillation there. Now, if you have a closed tube, such as a clarinet or an organ pipe, you can't have any oscillation at the end that's closed, and you have maximum oscillation at the end which is open. So that the simplest wave looks like that, with the big oscillation at the end and the small oscillation down by where the, at the closed end of the tube. If you have an open-ended tube, then the oscillation is maximum at the two open ends. This is a flute, this is a recorder, things like that. Higher pitched instruments tend to have these open tubes at the end. So, whereas the closed tube instrument, the deeper instruments, tend to have their shorter wavelength. Now, longer wavelength, I apologise. So, if you look at that, that's half a wavelength. It's only a peak. It's not the trough. It's only executing half the wavelength at any time, as is the bottom, because all it is you've cut it in the middle and shoveled them along, but it's still only half a wavelength. However, the closed tube, the reason it's deeper is because that same length of tube is only a quarter of the wavelength, only a quarter of the wavelength, because it's only the distance halfway up to the peak. Now we use this in the measurement of the speed of sound in air, an experiment we've already done. You can see there the antinode is just protruding above the top of the tube. That's quite important because it's important in the calculation. But the node is against the water. So we raise the tube in the water from 0 and hold a vibrating tuning fork over it. When the tuning fork and the column of air are at the same natural frequency, we get resonance. We hear a loud sound. That's resonance occurring. But it's the loud sound you're looking for, you see. And then you know that the two are at the same frequency. Now, the wavelength of the tube is the height of the wave plus the tiny little bit which is sticking out at the end, the antinode, which is above the end of the tube. And that depends on the width of the tube. So here is the formula for the wavelength. As you can see, we haven't just multiplied the length by 4, which is what we'd expect because it's a quarter of a wavelength. We've added on a correction factor of 0.3d, where d is the internal diameter of the tube. So the wider the tube, the more the correction. This is an empirical formula, unfortunately not to be found in the logbook. You have to remember this if you're going to do this experiment. Quite important. So the internal diameter times 0.3 plus L. Now, it's also very important to make sure they're all in the same units. The most common mistake made in this question is you put length in centimetres and the D's in millimetres, and you forget to put them in the same units, and you get a mistake. Big mistake. So, as I say, you take a tuning fork, strike it, hold it above the end of the tube, and you slowly rise it until you hear the loudest sound. And this is resonance, where the two natural frequencies are the same. And you measure the length from the water up to the top of the tube. Then you add on the end correction using a vernier calipers to measure the internal diameter of the tube. You use that formula, and then you use this one, C equals F times lambda. The speed of the wave is its frequency times its wavelength. Obviously, you can just stick the wavelength in like that. And then you do it for each tuning fork, and you find an average. Okay, harmonics. Whole number multiples are the fundamental frequency that happen at the same time as the fundamental. This are harmonics. When you pluck that string, you also produce some energy in the second and third harmonic. At the same time, the string is vibrating in the second and third harmonic to a lesser amount, giving it lesser percentage of its energy. Now, if you pluck the string down by the end, you increase the amount of energy given to the second and third harmonics, the fourth, the fifth, the sixth. Now, the interesting thing is, the first harmonic there has a frequency of, say, 100 hertz. The second, 200 hertz. The third one, 300 hertz. Yeah? Really? Is that difficult? Now, if you mix them all together, you sometimes get a strange pattern. This is a guitar pedal output where they've taken the first and second harmonics and given them the same amplitude. Rather rare. Well, impossible almost in ordinary musical instruments, and obviously electrical musical instruments not so much. And in this one, in fact, they've given the frequencies exactly a 2-to-1, as you can see by the key at the bottom. And you get this green wave, which looks rather strange, sounds really, really odd. It sounds a bit like automatic double tracking, if anybody ever plays the Korg guitar pedal. But very interesting sound, but it's made by combining harmonics. In fact, all musical instruments sound like they do because of harmonics. Now, let's take instruments like woodwind instruments, organs, things like that, where you have tubes involved. If both ends are open, then every time you go up a harmonic, you add another node. Notice there's only one node in the first harmonic. In the second harmonic, you've increased another node. And it's exactly one wavelength, that tube now for the second harmonic. You increase another node for the third harmonic. So you just increase nodes as you go up, and you get basically a wave of frequency 100, as I say, 200, 300. Now, if you have it closed at one end, it's slightly different. If you have it closed at one end, then you can only have a node at the closed end in the first harmonic. But the third harmonic, you see, the next one up, adds another node. Now, it's 3 times as long as the fundamental. Look at it. There are 3 quarter waves in it, 3/4 of a wave. So it's 3 times. So if the fundamental of clarinet is 100, its next harmonic is 300. And its harmonic after that, 500. We're still only adding one node, as you can see from drawing. Now, the best way to remember this is just remember how to draw them. I mean, to try and remember that you get first, second, third harmonic with open ends and first, third and fifth harmonics with a closed end, very difficult. But if you do get any question like this and you simply draw them, which you need to be able to draw these things anyway, you just have to remember, add a node. Add a node every time you go up in harmonics. For an open end, it'll create double the wave. And if you do it with a closed end, you get the first, third and fifth. So it goes up in odd numbers. Right, no idea what just happened there. It made a noise, nothing happened. There we are. Right, so these are the notes of a piano, except they're not the notes as you play on a piano. These are all C's and notes which are harmonics of the fundamental. So you hit this note, which is middle C on the piano, and the one on the far left will happen. The one on the far right will also happen. Now, the percentage of each of them decreases as you go left to right. But because of the piano key, hammer strikes the piano string very close to the point where it's held, it encourages other harmonics, which is why the piano sounds like a pleasant sound, compared with something where it's struck further up, or it's not struck well at all, like a zither, which just sounds like, two cats having an argument most of the time. This is an interesting one. Here you can see a piano and the different harmonics. This is for people who make electric pianos, really. You have the relative amplitude of your different harmonics. The blue line, the light blue, is the fundamental. That gives it the most energy, has the biggest amplitude. But the orange line, which is the first overtone, the second harmonic, is in orange, as you can see, is twice it. And then you've got the dark blue, which is 3 times it, the yellow, etc., going on and on and on. And then the other black lines not represented on the diagram show the size of the further harmonics. If you mix 5 harmonics together, or 50 harmonics together, you tend to get a reasonably shaped signal. The 50 is just put slightly higher. I think that's partly just to show the differences, which is not a great deal of differences. So the first 5 harmonics usually are enough. So if you listen to a reasonable piano sound electronically, it'll have 5 harmonics. You're listening to something and you think, is that a piano or is that electric? Then that's going to be 50 harmonics mixed together. It's the quantity and the size and relative amplitude of the different harmonics that how we tell different instruments apart. For instance, those people with very good ears can hear the difference between a violin and a viola. And the difference is not just the tone, because they can both play the same note. The difference is the mixture of harmonics, and you can see the harmonic pattern of the two instruments next to them. The violin is very strong in the fourth harmonic, whereas the viola is not. It is stronger in the fifth and sixth. And for this reason, people with very good ears can hear the difference. I, on the other hand, spent a lot of my youth very close to the speakers at some very loud concerts and cannot tell the difference between either of my daughters when they're speaking. Right, so a stretched string. A low note, for instance, on a double bass contains all the harmonics above it. And this is what gives the instrument its pleasant timbre, quality of the note. It's a mixture of the harmonics. That's what I was trying to explain to you. So, and this is largely due to the fact the string is slightly slacker and so can produce more harmonics. Now, the string formula gives us our experiments. First of all, the formula is in the logbook. This one is, and that's why you don't have to remember what graphs to draw in these Section A questions. Because as you can see, frequency is inversely proportional to L. It's in the logbook. So we plot F against 1 over L for that experiment. Whereas if we have frequency against tension, you can see the square root above the tension in the formula. So you plot frequency against the square root of tension. It's not rocket science. It's all there if you know where to look for it. So this is the first experiment. You've got the length, you've got the bridge, you've got a little paper rider, vibrating tuning fork. At the point of resonance, the little paper rider jumps off, and then the frequency of the string is the same as the frequency of the tuning fork. If you're asked for an example of resonance, by the way, you can draw this diagram. It's a perfectly good diagram to explain resonance to anybody. I've got another one later, but this one's just as good. It's an example of resonance because the paper rider jumps off because of resonance. Okay, so you place the bridges a long way apart, strike the tuning fork, put it on top of the bridge, on top of the string, and then you move the little bridge until the paper rider, the very light paper rider, jumps off. You can almost call that a precaution, the fact you have a light paper rider. You measure the length with a meter rule. Remember, you've got a meter rule. You've got to avoid parallax when reading the meter rule, so there you have a precaution. You note the value of the frequency. Find the value of the tuning fork. How do you find that? It's written on the tuning fork. A number of people can't answer that question. It's written on the tuning fork. Repeat for different tuning forks. Draw a graph of what? Of what? Frequency against 1 over length. Frequency against 1 over length. And you'll get a straight line through the origin. If you don't get a straight line in the origin, you have done something wrong. Do not hand it in and say, it'll do. It won't do. Draw it again. Now you can also do the same experiment without measuring length, but tension, by increasing the weights that are making the string tight. So you vibrating tuning fork and you keep adjusting the weights until the paper rider jumps off. And then, that's what that's saying. You just adjust the weights, and the weights are the tension. So they are what you plot, the weight for tension. And then you plot force against the square root of the tension, i.e. the square root of the weights you put against it. Finally, what are musical notes? What's called their characteristics? Now, I am getting a bit sick of people writing the characteristic of music note is, it's pleasant, man, I like it. Or the characteristic of music is, it gets people really happy. No! Physics actually has definitions for all these things. Music is a regular shape note. And there are 3 qualities of these musical notes which are called its characteristics. The first one is pitch. This is the frequency of the wave. If someone says, what's the pitch of the instrument? I mean, what frequency does it vibrate at in hertz? Loudness. Loudness! This is the amplitude of the wave, how big the wave is. What's the difference between the peak and the centre line? That's the amplitude. In music, we call it loudness. And finally, the one I've already mentioned, timbre, or quality, we can easily say. It's the shape of the wave. And the shape of the wave is formed by the number of overtones, by how many harmonics are mixed with the fundamental wave to give it a slightly different shape from the usual sine wave that you are looking at. So we're going to look a little bit at resonance, as I said. First of all, what is it? It's the transfer of energy between two objects with the same or very similar natural frequency. And what we're going to use is Barton's pendulum. Barton's pendulum is basically a string strung between two points, and from the Barton's pendulum are different weights all hung. Two of them, the one at the end and the fourth one along, are the same length. So what happens is, as you set the one on the left oscillating, it's called the driver, it transfers its energy to the one of the same length without affecting the others. And the energy basically goes backwards and forwards between those two. Not as quickly as this, obviously, it takes some time. So we've got resonance, perfect transfer of energy between two bodies. We've got musical notes with its characteristics of pitch, loudness and timbre. We have lots of things. Go back, listen to it again if you couldn't follow. This is the question set, question 3 from 2014. It's obviously a question using the sonometer, frequency against the stretched string, as it were. Try this question out. Get back to me. That's the end of the talk.